So this is problem 5 on homework 2. This is just the wave equation with c equals 1, and with the initial conditions that u is identically 0 at time 0, and its time derivative is the characteristic function from -1 to 1. Um, so this is just wave equation on an infinite domain. So we can apply D'Alembert to get the following solution. And we're asked for an explicit formula for x greater than 1 and arbitrary t. So the first thing to note is that u is odd as a function of t, right? Because when you input negative t here, you just flip the bounds of integration. But you can again flip the bounds by introducing a negative sign out in front. So this just gives us negative u of xt. Right, so it suffices to consider time greater than or equal to 0 because we can extend our solution in negative time uh, by introducing a minus sign out in front. So let's look closer at our solution given by D'Alembert. Um, so we can rewrite this as an integral on all of R uh, by multiplying the first integrand by the characteristic function on the domain of integration. So characteristic function on the interval from x minus t to x plus t. Right, because inside this interval, this is exactly equal to the first integrand. And outside of this interval, uh, this is just 0. Um, so the good thing about this representation is um, when you have two characteristic functions multiplying one another, this is just equal to the characteristic function on the intersection of the two supports, right? Because when y is contained in the intersection, y is in this interval and in this interval. So this will spit out 1, this will spit out 1, and this will spit out 1. Um, and if y is not in the intersection, this will spit out 0. And y not being in the intersection tells us that y has to be excluded in at least one of these intervals. So at least one of these characteristic functions is going to spit out 0. Right, so we have genuine equality between these two integrands. So now the good thing about this is that when you're integrating a characteristic function on R, this will just give us the length of the support. So this just becomes a matter of measuring the um, intersection between these two intervals. Right, so let's draw a picture to understand what's happening. We have this characteristic function from -1 to 1. We have some x that lies somewhere outside of this to the right. And we're expanding in both directions by some quantity t. Right, and we're interested in um, the intersection between these two intervals. So it's clear that we're going to end up with 3 cases. I've drawn the first case here. This is when x minus t is greater than 1. Here, their intersection is empty. So u is just going to be 0. In case 2, this left endpoint is going to be somewhere inside -1 to 1. right? So their intersection is going to be this bit here, the interval from x minus t to 1. So u simplifying from this line becomes the integral on r of the characteristic function on x minus t to 1. And when you're integrating a characteristic function on r, this just gives you the length of this interval. So we have this. And finally, in the third case, this left endpoint is somewhere to the left of -1. Right, so here the intersection is just all of -1 to 1. So again, this is case 3, where x minus t is less than -1. And again, continuing from this line here, u of xt becomes the characteristic function on all of -1 to 1. Again, this just spits out the measure of the support. In this case, it's the length of this interval, which is 2. So we end up with just 1 in this case. All right, so putting this all together now, for x greater than 1, t non-negative, we get that u of xt is equal to 0 if x minus t is greater than 1. 1/2 of 1 minus x plus t if x minus t is between -1 and 1. And it's equal to 1 if x minus t is less than -1. So we can do a bit better than this. We can rewrite these inequalities as statements about where x is. So this is equivalent to saying that x is in the open interval from 1 plus t to infinity. The second condition is equivalent to saying x is in the closed interval from -1 to, -1 plus t to 1 plus t. And this third one, we have to combine this inequality with this to rewrite this as x in open 1 to -1 plus t. Right. Now this last inequality, looks kind of weird because, for example, what happens if t is less than 2? In this case, this just ends up being empty, and these two intervals span all of x greater than 1. So this is actually fine. But this is only for t greater than or equal to 0. To extend this to negative time, we use the fact, which we showed earlier, that u is odd as a function of time, to extend this as follows. Right, so let's clean this up. So for positive time, we have this. And for negative time, we take an odd extension in time. And this gives us the following. Right, so this is the solution. Now for the sketch. So let's draw the xt plane and introduce a third axis for u. So at time 0, as the initial condition specifies, u is just 0. At time 1, u starts off at a height of 1, and it tapers down to 0 like this. Then at time 2, it again starts at a height of 1. But it stays at 1 until it reaches x equal 1. So this is x equals 1. And then it tapers down. Then at time t equals 3, similar story. Starts at 1, stays at 1 until x equals 2. And then it tapers down. Right? Then at this point, the sketch is getting a bit messy, but as we stated earlier, u is odd as a function of time, so you can just extend this into negative time. Yeah, this is very messy. But it should look something like this. Right, so the problem asks for a sketch of u as a function of t. So that'll look like slices in this direction. So we're fixing x and we're watching u vary in time. So here, the picture is kind of like this, where this is 1, this is negative 1, and this is t equals x. Right, so this is the sketch.